Hi, Barton Marchand. We hope you guys are well. We know a lot of kids are sick. Hope you guys are doing okay. Tell you what, kind of strange that this video is actually going to be very short because we've got a part 2 and a part 3 video that pick up after example 1. So however I did that in the past, I don't know why that happened, but we're making this video right now just to introduce this section and then going on to example 1. So today we're going to find a tangent plane. We're going to go back to an earlier concept, and so much of this chapter really does do that. When you will look back on this whole chapter, lots of older material comes back into our final unit. So we're going to get a tangent plane. Remember, what we talked about before is we could have a parametrically defined surface from a vector function. We could have all these different arrows coming out, and the tips of the arrows could create a surface. It might be a sphere, it might be a cone, it could be a paraboloid, you name it. And here we have a picture of that surface. Remember, we had grid lines also holding u or v constant, and u and v, of course, were just these arbitrary names. They could be phi and theta. They could be, x and y, in fact, as we saw before. But let's just say we're holding these, vectors or these constants, for u or v for one of the parameters. What we could see is if we went ahead and found the partial derivative of r with respect to u and the partial derivative of r with respect to v. Again, remember, looking at these curves, you can see a C1 and a C2. If we're just going to take our derivative holding one of those parameters constant, we're going to get those two vectors right there. This should seem very reminiscent of what we did earlier in the class. We could say, well, my goodness, if I wanted to get a normal vector to that plane, we took the cross product of the vectors to do that. We took the cross product. So as long as your cross product is not 0, the surface is going to be known as smooth, having no corners, and we can use that cross product as a normal vector to the tangent plane. So let's do example 1 together. It says find a tangent plane to the surface. And my goodness, you don't even need to know what that surface looks like. It's not like you're asked to make a picture necessarily. But one thing that you are going to notice rather quickly is that, our x is u squared, our y is v squared, our z is right here. So we could say r, that function, in terms of u and v, would be, of course, we'd have u squared for our x component, for our I component. We'd have v squared for our j component, and then we'd have u plus 2v for our z component, or for our k component. And, this right here, if you let u and v span across real numbers, you could generate a surface, but they're giving us a particular point that we'd like to, get a tangent plane equation written for. But let's go ahead and see if we can get that normal vector, and we're going to have to do that by taking some partial derivatives. Let's take our partial derivative with respect to u. Now, what do we get when we do that? Well, first component, our I component, we just get 2u. How about our j component? That's 0. And then how about our k component? That's just a 1. And that's not so bad, right? And then we could say, well, similarly, we can go ahead and take our derivative of r with respect to v, holding u as constant. What's that first component here, taking the derivative of u squared with respect to v? We get 0. Then we'll get 2v, and our k component will just be a 2. You could say, well, hey, look at that. Now, you might wonder about finding the cross product. We definitely could do that via the calculator. That's fine. But what you probably did to start off was to, just remember at the beginning of the course, going way off to August, if you can believe that. So very, very long ago. And, what you did is you just wrote out the two vectors that you were looking for, and then you did the determinant of those two vectors in this format. That's really what the cross product is. So, doing either the basket weaving method or the method that we had seen previously, look, if I just looked at our i's, we'd, cross multiply, we'd get 2u minus 2v. So you could even write that in that regard, maybe write it as an I right here if you'd like. But then we'd have to write a minus if we're going to do some cross multiplying. We'd get 2 times 2 is 4 and 1 times 0 is 0. So we'd get a minus 4j right there, right? And then for our k, as we're looking at, how we're going to do that, yes? Oh, it's 2u for, this right here, and then minus 2v. Yeah, so that... Oh, did I miswrite this? It was 2u and then 0. So sorry. Let's fix that up again. I miscopied that. So sorry. It's actually going to make our problem a little bit simpler, isn't it? Thank you for catching that. Sorry for the mistake. You're looking at our I here as we cross multiply. This would wipe out to 0, and then we'd minus a 2v, right? So we've got that. And then, as we look at the minus in the middle, that would be just a 4u if we were to do that. Again, what's happening is you cross out the I component, and then you cross multiply, you get 4u minus 0, right? So it's 4u, and that would be with your j. And then, for k, well, as we try to clean that up, and thank you so much for catching that. For k, it's like we're crossing this out. This might be the messiest one. It's back to a plus, and we'd have, let's see, 2u times 2v would be a 4uv, and that would be your k. So, right here, guys, what you can see pretty fast is that cross product is going to be writing that out, negative 2v, negative 4u, and 4uv. And that's going to be our normal vector. That's going to be our normal vector. But, of course, we're going to have to plug in the appropriate values of u and v. So, that's why they gave us the 1, 1, 3. The 1, 1, 3, you could say, well, x right here is u squared. And, our v is representing the y is equal to v squared right here. And then we'd have u plus 2v over here for our z, right? So let's think about this. What could we maybe choose for our u value here? Our u value we'd probably choose to be 1 or a negative 1, right? Kids could say, couldn't it be 1 or negative 1? You're right. A v could be a 1 or a negative 1, but I'm going to choose them both to be positive so that when I'm plugging that in for my z component, I get my 3, right? Because I'm going to have to find this normal vector, so I'm going to plug in u equals 1, v equals 1, so our normal vector is going to become negative 2 times 1, so that's negative 2. We'll have negative 4 times 1, that's negative 4. And then this is 4 times 1 times 1. That's just a 4 also, isn't it? Okay? So that's going to be our normal vector. Now, guys, as we're looking at this, of course, you could most definitely use this exactly as your normal vector. Normally, we had the equation of a plane was A times x minus x naught plus B times y minus y naught plus C, times Z minus Z naught. And we set that equal to 0. Well, guess what? Your normal vector is your ABC right here, you might remember. And the point in question was a 1, and then what was it? I guess a 3, right? That's your x naught, y naught, z naught. So I could say it's negative 2 times x minus 1. And then what? Plus a negative 4, or just minus 4, y minus 1. My c would be a positive 4, and we could have z minus 3. And this right here is a possible answer that we could have for the equation of the plane. We could definitely use that. And, you could also have reduced your normal vector. You could have divided everything by a 2 or even a negative 2, and you would have gotten a similar answer. But that's really how you write the equation of a plane here. We doing okay? All right, we're going to wrap up this video right here.